Hi, today we want to speak about the elementary data structure. In first step, we don't want to go in details how to handle with data and how to store it in our memory. So first we speak about the abstract data type. In this concept, we try to explain the data behavior and also the corresponds function of it. And then when we better understand the data behavior and data function by the abstract data type concept, we think about the implementation of ADT, or we think about how to store our data in our memory, and it makes our data structure. So first of all, what is the abstract data type or ADTs? We have two main ADTs. One of them is stack and the other is queue. The stack and queue has differences, and based on these differences, they made two different abstract data type. These differences are in their behavior and their corresponds function. What's a stack? A stack is like dishes or glasses. Think that we have some dishes or glasses that we put them up to each other. Then when you want to pick a glass or a dish, you can't have it from the middle of these dishes. You must pick it from the top. And if you want to put a dish on them, you must again put on the top. So a stack is like this, means that you just can add the data on the top of a stack, and when you want to return a data or delete a data from it, you can just delete or return just the top data. You cannot have from the middle of the stack. We explain this behavior as LIFO, or last in, first out. And based on this behavior, we have two functions. One is the push function and the other is the pop function. Push function means that adding an element to the stack. As I said, you must add it on the top, and we consider the top of the stack by the s dot top. You can see here the definition of this function. This definition is like a sketch of this function, and based on the your programming language and your implementation, your coding will be a little different, but the main core of the code is the same and is based on this function. As you can see, we say that okay, you must consider the top of a stack one element more, and then we say now consider on the top the element x that we want to add it. And the pop function is to return an element of from the stack. And as I've said, we can just have the first element. So first of all, in pop function, we check that the stack is empty or not. If the stack is empty, so there is no element in a stack to return, and we will have an error. But if there is something there, we say, okay, consider the stop one less, and then return what was in the top. So by push and pop, as you can see in this slide, we have the LIFO behavior of a stack. As I've said, we have another kind of ADTs, and the other type is the queue. The queue is like that you think you are in the airport, and we have some different people that want to um, fly, for example, to London. In this example, the first person in the list, the first person who comes, for example, to check in, will be the first person who receives the service. And in the equipped ADTs, the first element that goes to the queue will be the first element that comes out. So what it means? It means that the data comes in following each other in the queue. And we can say that we have the FIFO behavior, means that first in, first out. And based this behavior, we have two other functions. One is enqueue and the other is dequeue. Enqueue means adding some element to the queue. How it happened? As you can see here in the code, first of all, we have for queue one tail and one head. We say to the code that let the tail of the queue be the element that I want to add it, x. And then we add a number to the tail of the queue. So we consider x at the end, at the tail of the queue. And the dequeue function is to return an element from our queue. In this returning, we say that, okay, first find what is on the head of the queue and store it in element named x, and then return this x to us. Now we know two ADT types, and we know the corresponds function. It's time to think about how to store data in our memories. To implement the data structure, we have two ways. One is array and the other is linked list. What is the differences between these two implementations? The array. The array is like that. It has a constant size. It means that, for example, when we want to store five value, we go to our computer and say that we want to call 5 cell of our memory as the array, for example, named A, as you can see here. And then we put our data or our value in the cell memory, because we consider exactly the cell memories and the array size is constant. So when, for example, we have an array with size 5, and all of the cell memory of this array is full, then when we want to add another value to the array, then we will have an error. To do it, we must resize our array. And it means that we have the resizing process. In resizing process, the cost of the resizing process each time will be O(n). And think that we have different function, and when we have a lot of function and we need a lot of resizing, then it can dramatically become so dramatically bad, and it makes us the resizing problem. Why? Because this resizing make the complexity of algorithm dramatically bad. In this situation, we use a technique that's called amortization. What is it? It's a technique that say that when task T costs so much and we want to simplify it, we change this task to, for example, n task T1 to Tn, and then the cost of the task T become the average of cost T1 to Tn, and it means that we can control the complexity of our algorithm. We can control the cost of this action. And the amortization in the resizing problem is that each time that we want to resize our array, we make double array size. And by this, we can control the resizing problem and the complexity of our algorithm. It means that if the array A has size x, then in each time that we want to resize it, we make it double. We make it 2x. And then by this, the complexity of algorithm will be controlled and we will overcome this resizing problem. The other implementation of our ADTs is another data structure that's called linked list. Linked list is, as you can see its presentation, we have a memory, and in each memory we have different memory cells. In linked list, for each value, for each data, we make a nodes. Node 1, node 2, and the others. And in each node, we consider two cells of memory. One cell is for the value that here is 1, and the other cell will be for our pointer. The pointer shows the next node for us. And we have also a head pointer and the last pointer that goes to the null to show that, okay, where is the head and where is the tail of our linked list. We have different type of linked lists, as you can see here. One is a circular linked list and the other is a double linked list. In circular linked list, the last pointer goes to the first node, and in double linked list we have two kinds of pointer. One pointer points to the next node and one pointer points to the last node. By this linked list structure, we can overcome the resizing problem. As I've said to you, because the array size is constant, so each time we want to add more value to the array, to the full array, we need to resize the problem. But by the linked list structure, we can overcome it. How we do it? It will be by two functions, list insert and list delete. You can see the codes here. Now I want to explain what this code means. We want to add, for example, the value for between two and node, between node 1 and node 2. Consider that the head node index is 0. I want to add the value for between node 1 and node 2. How I will do it? First of all, I will consider a node. This node must have two memory cells. One is for value, that is 4, and the other will be our pointer. Now, how the list insert works? First of all, it delete the previous pointer of 2, and then it change it, and 2 will point our new value 4, and then we define the pointer of value 4 to node 2 to value 3. So by this simple construction, we can add so easily the value 4 to our linked list, and we don't need any resizing, as you can see. And how the deleting happen? For example, we want to eliminate the node 1 value 2 from our linked list. First of all, you must check that, okay, node 1, where is node 1? If it's in the head of the linked list or in the tail of the linked list, then you must do something different. For example, we have a linked list like this. We have 1 goes to 2 goes to 3, and I want to eliminate, to delete the first node, the head node 1. When I want to delete it, okay, I remove it, and then the head pointer must point the next node 2. So here you can see we define it in the list delete function. And in the next example, think that we have it and we want to delete 3. 3 is in the tail, and when it deleted, the pointer of 2 must now change and it must point to the null. Again, we consider this special situation by if-else statement, and in a completely usual structure that we have node 1 goes to node 2 goes to node 3 goes to null. If I want to delete the value 2, I just delete it, and then I must change the pointer of 1. Instead of pointing 2 that is deleted, the 1 must point the next node that is 3. All of these situations are completely explained in our code by if-else statement here, and it will be the list insert and list delete function that help us to overcome the resizing problem of array. But maybe you asked why we don't use the linked list instead of array. Because the linked list has advantage and disadvantage. The advantage is that we don't have a resizing problem. We can easily by the pointer adding or deleting an element. But the disadvantage of linked list is that, for example, we have a long linked list and we want to find an element in it. You cannot easily go through it and pick it up. You must from the first node start and check all the nodes to find the spatial value. It means that the cost of finding an element in linked list is so much. And the other problem is that, as you can see here, for each value in linked list, we have 2 cells of memory. One is for the value and the other is for the pointer. It means that when we have a large data set, then it costs a lot of memory cell, and it will not and fast implementation. It will become dramatically slow, and because of this advantage, we don't use linked list always. But it has its advantage, and we must consider what is our problem, and then we must choose the good and appropriate implementation in our spatial situation. Now, at last, I want to just mention a spatial case. As we have spoke about the linked list, we have pointers. In high level programming like Python, you don't work at all with the index. All things happen in background. Means that, for example, when I say in Python that the A is an, for example, array that 1, 2, it's array or list 1, 2, 3, and then when I say B is equal A, then all this considering the memory and all this allocation, all this pointer, all things in Python happened in background in high level programming. But in some cases, for example in language C, we must manually work with our pointers, and in this language, in this programming language, we access to the exactly address of our memory. We have function that we can call an exact address of our memory, but it isn't usual things in low-level programming. We have low-level programming language that we don't access to the address of our memory. So when you don't access to the address of your memory and you want to implement a data structure, uh, and you need to define a pointer, and you cannot and you don't have a function to access these addresses. uh, what you must do in this situation, we use a technique that in this technique we use the index instead of our pointer. It's our technique. How it happened? Instead of a pointer, we consider three array, where one array is our k, that all the values will store in the k array, and the other array will be the next, and in each value we consider the index of next node in the index array, and the third array is the prev, that we consider the index of a previous node of each value in the prev array. And by considering these three array, and we can easily make a pointer for each node for in the low level programming language, that we don't have access to the address of our memory cell. So just have it in your mind that if in such a special situation you have a low-level programming language and you want to define the pointer, and you don't access to the address of your memory cell, you have a way, and this technique is the index technique. Just define three array, and in each node, each value when you want to store, you must consider these three array, and by this you will have your pointer. You simulate a pointer by this index technique. Next time we will go further and speak more about the data structure, and I think in the next episode we will speak about the sorting and different sorting function. Until the next time, have a good day.